Okay. Yeah. So, good evening to all the students and welcome to NPTEL program, week 5 of Electrical Machines 1 tutorial. So, I am Sai Krishna. So, yeah, I am your Electrical Machines 1 TA. So, for the last 4 weeks, we have discussed different topics on transformers, and this week we will be discussing about three-phase transformers. Inside three-phase transformers, we will start with very basics, like how we can build a three-phase transformer using three single-phase transformers, and we will see some different kinds of connections in three-phase transformers, like star, delta, delta star, star, star. So there are different kinds of connections, and we will discuss a little bit of concepts on this, and we will solve a numerical so that uh, we will understand this whatever we discussed in the topics thoroughly. Now, let me put it in the presentation mode. Yeah. So let's start with discussing about three-phase transformers, and in this we will see first how we can build a three-phase transformers using a single-phase transformer. So yeah, okay, yeah. So let me start with a very basic thing we know. We know for a single-phase transformers we have our kVA rating and high voltage side, low voltage side, and the frequency at which our single-phase transformer is operating. Let's take a single phase transformer with known ratings and let's see how we can construct a three phase transformer out of it. Now, see that. One second. Someone has joined. Let me admit. Yeah. So, that today's topic will be three. Three-phase transformers. Okay, so there are two ways to build a three-phase transformers. Either you take a three single-phase transformers and do suitable connections to it so that you will get a three-phase transformer, or you can directly use a three-phase single transformer as a single unit. So yeah, three numbers of single-phase transformer that which you call bank of three-phase transformers. Now, if you are using three individual single-phase transformers, you call it as a bank of three-phase transformer, or another way is using one single unit of three-phase transformer. Now we are going to discuss this way, where we will be taking three single-phase transformers and we will doing the suitable connections between those three transformer windings so that we will get a three-phase transformer. Now let's take. I'm writing my single-phase transformer ratings. It is 5 kVA. HV side is 200 volts, LV side is 100 volts, and 50 hertz transformer, that is single phase. So this is the single phase transformer I took, and let me draw the primary winding of first single phase transformer. Now let me draw my secondary winding parallel, like this. Usually we have like transformer connection side by side. I am drawing now in this fashion. So yeah, let me draw the primary winding of the second transformer, secondary winding of second transformer, primary winding of third transformer, secondary winding of third transformer. Yeah. Now let's mark the terminals for high voltage side and low voltage side. Yeah. Let me admit. Yeah. So let's mark the terminals first. So to be clear from our side. So okay, this is primary side. This is secondary side. Which side is HV? Which side is LV? We have to be clear that. So I am using capital letters for HV side. Okay. A1, A2, and yeah, secondary side will be, I said, LV side we will using small letters, small A1, A2, and yeah, the second transformer B1, B2, B1, B2, capital C1, capital C2. Yeah, so the secondary will be small c1, small c2. Okay, so we have used capital letters for our HV side, high voltage side, and small letters for LV side. Now one more important thing is to mark the dot polarities in each side. So polarity marking is very important considering a transformer, because we need to know where the current is entering from where the current is leaving. So yeah, we already discussed how to get the polarities. Like we will do some simple polarity test and we will see where the current is entering and where the current is leaving. So yeah, let me just mark my polarities here. Polarity marking is very essential. So yeah, now so let's see what are the rated voltages I'm writing. What are the rated voltages? 200 volts and 100 volts. Now let's calculate. Let's suppose now I'm connecting my HV side to a three-phase balanced supply. Let me denote my supply here. So I'm connecting A1, B1, C1 to my supply. I'm denoting supply by AS, BS, CS. This is my three-phase balanced supply. I'm connecting it. So yeah. Before going into more analysis, let me just write my rated currents. So we know how to calculate our rated currents at each HV side and LV side. So we know the ratings of the transformer, we know the kVA rating, and we also know the HV side voltage and LV side voltage. From that, we can easily get the rated currents in both high voltage and low voltage side. Now, what is the kVA? It is 5 kVA divided by what is the HV side voltage? It is 200 volts. Now, yeah, it is 25 amps. Now, similarly, calculate the low voltage side rating. Same, 5 kVA divided by what is the voltage in LV side? It is 100 volts. Now it will be 50 amps. Okay. Now we know the ratings of the entire three-phase transformer. So individual winding, how much voltage should I apply, and individually how much currents should pass through each winding. And now I know the ratings. Now let's say I have connected now I have also connected my primaries to the supply, and now I want to connect a star connection. So since my supply is AS, BS and CS, and the supply phase sequence is AS, BS, CS. ABC is my supply phase sequence. And yeah, to get a if I need a star connection, I will short one in each in each single phase transformers. I will short one terminals, everything. I will force three terminals of each transformer to be at a single potential, and that will give me a star connection. No, the rest, the free terminals I will take as input, or I give a supply. So yeah, now I have shorted A2, B2, C2, and so this is a star connection. So I know the individual voltage that the maximum individual voltage that should be appear across the windings. So since this is HV winding, I know that each A1, A2, B1, B2, C1, C2 should only see 200 volts or less than that. So I can't go beyond 200 volts. Now, since I can apply a supply here, so this is my line to line voltage, and this is nothing but my phase voltage, and yeah, this is my line to line voltage. Now, in a star connection, we know line to line voltage is root 3 times the phase voltage. So how much voltage can I apply here so that my transformer won't go overrated? Since my voltage at every winding is 200, okay. Okay, yeah. Since my 200 is the rated voltage on the HV side, I can only apply. Okay. Yeah. My line to line voltage will be 200 multiplied by root 3. Yeah. Since my phase voltage will be 200 root 3 by root 3, then I will get a 200 volts. So I know that I am giving only rated voltage across the windings of my transformer. So that if I give 200 root 3 voltage at the supply terminals, so I can say that 200 volts can come across the transformer windings, and the rated conditions I can apply. Now, yeah. So let's connect the secondary now. So we haven't connected secondary. Before connecting secondary, let me just draw the phasor of my primary. Since my supply AS BS CS is a phase sequence of AS BS CS, it's a three-phase balanced, and it's we have connected our primary in a star connection. I'm just marking. So A1 is nothing but, from the diagram you can see A1 I connected to AS. So A1 is nothing but AS. So A1, A2 I have, let's say this is B1. Since it's the balance supply, each phase will be displaced by 120 degrees. So the angles here will be 120 degree apart. So each phase will be 120 degree apart. Yeah. Now this is B1. B1 is nothing but BS, that is supply, and this is B2, same point, and this is C1, which is nothing but CS, and this is C2. Now, since we shorted A2, B2, C2, we are forcing those three points should be at the same potential. We have shorted that. So that's why A2, B2, C2 are in this time. So yeah, three-phase balance system. These are 120 degrees apart. Now see, even whatever connections we make, every rule of single-phase transformer should apply here, because in fact we are using three single-phase transformers to get this connection. So all single-phase transformer rules will be applicable here. So we know whenever yeah, if at all I have given 200 volt supply to my individual winding by the transformer principle, I am sure that whatever the LV side voltage here, 200 volts by 100 volts is my rating of the transformer. So the instant I give 200 volts to my primary, I can say for sure that 100 volts will be induced in the secondary volts. So if you see this 100 volts, 100 volts, 100 volts. So I'm sure, because it's a transformer principle. So 200 volts, I have made sure by giving 200 root 3 as my line voltage, 200 volts in individual phase I can get. Once it is 200 volts rated, in the secondary I can get 100 volts as rated. Now it will be in parallel. Let me draw the phasor of secondary also. Since I have not connected any kind of connection in secondary, you can see there is no connection between these three. Now all these phasors are isolated. Let me draw.
Sir, sir, HV side winding is connected as look like a starter connection.
Which connection?
A star connection.
Yeah, which side?
HV side,
HV side is star, right?
and secondary that means LV side. Which type of connection,
Yeah,
sir?
we have not gone to that part. I haven't connected secondary side. I will be. We will go to that. Which connection will be making?
Okay,
First,
okay.
first I will be discussing star star only. But right now I haven't connected my secondary. That's what I'm going to draw here now. Okay. Yeah. So see, since according to my transformer action, I will say that my two voltages in the primary and secondary will be in phase. The induced voltages will be in phase. So A1, A2 in this fashion. So now my A1, A2 will be parallel to my primary voltage, HV side voltage, and magnitude. So let's say this magnitude is 200 volts. So this magnitude will be half of it because it's 100 volts only. Yeah, sorry for that. So I am not the scale is not exactly half here, but keep in mind that the magnitudes will be half. The phasors magnitude will be half because 200 is my HV side, 100 is my LV side. I'm just yeah. Now yeah, we can see B1, B2 in this fashion. Now my secondary induced voltage phasor will be in parallel and in phase with that primary HV side phasor. So I know B1 and B2. Okay. Now same thing with C1 and C2. Yeah. So yeah, these are my secondary phasors. Now I haven't connected any connection, but even before connection, I can say that how my secondary phasors would look like. Yeah. So now in secondary side, let me short these three. Now I have shorted A2, B2, and C2. The moment I connected these three, so now from the phasors you can say that these are no longer isolated. So previously these three windings are individually isolation is there. Now I have shorted A2, B2, C2. I have forced those 3 points to be at the same potential. Now these are no longer isolated. So yeah, once I shorted A2, B2, C2, my secondary also became as yeah. We will discuss three-phase problems, Vinod. Once, once let me discuss star-star connection and one star-delta connection, and we will do numerical problems on star delta and delta star. Okay. Yeah. So yeah, once the moment I shorted A2, B2, C2, my secondary also became a star connection. Now, yeah. So let me now now I'm just moving my phaser to here C1, C2 because A2, C2 at same potential. Now I will move my this phasor to here B1 and B2. So this is how my secondary phasor look like when both primary and secondary are in star connection. So primary is star, A2 B2 C2 I have shorted capital A2 B2 C2. In secondary LV side I have shorted small A2 B2 C2, and that's how my phasor diagram will look like. Now one more point, I have applied 200 root 3 at my supply side, that is line to line voltage, so that my phase voltage would be 200. Now once my 200 voltage flows through my primary winding, so 200 volts, 100 volts. Now yeah, the secondary I had I got 100 volts, And yeah, now this particular whole connection, sorry, some network glitch has happened. Okay, let me share my screen. Yeah, so so this is my three-phase transformer connection. This entire connection I call it as three-phase transformer connection. So now I want to bring my output terminals. So what is my output terminals here? Small a1, small b1, and small c1. Now just drawing it quickly. This is the primary star I have connected. So this is my secondary. Now I'm bringing okay. This one is A, this one is B, this one is C. Now I'm taking this output terminals. This will go to a three-phase balanced load. So yeah, now VHV side, what is my line to line voltage? It is 200 root 3. Now my low voltage side, what is my line to line voltage? 100 root 3. Because we know already it's a phase voltage as 200 and 100. Now these are my line to line voltages. Now yeah, let's talk about loading now. Just right here. Now I have connected my terminals. So this is A and this is B and this is C phase to a three-phased balanced load. So what is my supply here? This one is a supply, right? 200 root 3. Supply here, and this is 200 here, and this is 100, and my line to line voltage at the output side will be 100 root 3. Yeah. So can anyone tell me what kind of current will flow when the moment I have connected the load? It will draw whatever amount of current based on the load. Now, once I will connect three phase balanced load, the load can be anything. The load can be star connected load or load can be delta connected load. The only restriction which be the maximum amount of line current that should flow through the windings is restricted, because in the previous slide, see, 25 amps is the rated rated current that should flow on HV side, and 50 amps should be the rated current that should flow on the LV side. Now coming to this side, so this is LV side and this is HV side. So the maximum amount of current that should flow in this each line, because in the star connection, line current is equals to phase current. So my LV side 50 amps, 50 amps, 50 amps. So yeah, only restriction is the load can be any kind, but the restriction is we should not allow more than 50 amps to flow through the secondary side. So once 50 amps flow through my secondary, once 50 amps is coming out of the dot polarity from this one dot polarity, so I can say for sure that 25 amps must be drawn from the supply. AS, BS, CS. Yeah, yeah. So this is all about current. So since in star the line current and phase current are same, the same current will flow through each phase as well as the line current same. So 25 amps and 50 amps. That's the restriction I am placing on the uh, currents. Now let's talk about kVA. So let me write. What is the total kVA? Total kVA will be, so it doesn't matter what kind of connection you are making in a transformer, whether it is star star, star delta, or anything. Your kVA will be, if you know the line voltages at both sides, the kVA will be root 3 line to line, I line to line. So we can do it in both sides. Let's say in primary side. Primary side will be, in our primary side is HV side, right? So root 3 into line to line voltage of high voltage. How much is line to line in high voltage? That is 200 root 3. 200 root 3. Now what is the line to line voltage in high voltage side? That is 25 amps. Now how much this will be? 50, 15 to 3, 15 kVA. Now we can also tally with this secondary side. You can also calculate the total kVA from secondary side as well. Let's see what it will come. So secondary side line to line voltage, the low voltage side is this one, 100 root 3, and the current, the rated current in the low voltage side is 50. Now it 50 into 3 into 100, it's again 15 kVA. So kVA should always be balanced, because that's the rule. Whatever kVA supplied should be delivered to the secondary side. We already saw that in the last week discussion as well. So if you see, the total kVA turns out to be 15 kVA. So that individual phase transform, individual windings for each phase, we can say it is around 5 kVA, right? Exactly 5 kVA. So that's also the single transformer which we picked up during starting of the session. We picked the transformer which is a 5 kVA rating. So we see that has been balanced. So we all maintained all the ratings on the both sides, and yeah, that's it. Now let's look at one last connection. We will look, that is star delta, and we will solve the problem now. So we'll quickly see the star delta connection. Now let's see. Again drawing the primary windings of three single phase transformers and secondary windings of my each single phase transformer, and yeah, A1, A2, A2. Now I am giving supply A1, B1, C1 to AS, BS, and CS. Don't forget about the dot polarity. It is very important. Yeah. Now how much I am applying here? Star, right? I will short A2, B2, C2 and apply 200 root 3 line to line. Okay. So yeah. So before going into delta connection, let me just quickly draw the phasor of primary, because primary I already connected in star fashion, and yeah, we already see the primary before. A1, B1, C1. So A2, B2, C2 are at common potential. Now yeah, so the length of each phasor will be 200 volts, because okay, 1 second. So yeah, so the length of each phasor will be 200 volts. So yeah, I am just drawing the induced voltages in the secondary side, A1, A2. Now here the length will be 100 volts. Length of the magnitude will be just half, and yeah, B1, B2, and C1, C2. I haven't connected these secondary phasors. That's why I draw it in isolated phasors, since this is isolation. So yeah, how does a delta connection look like? So let's say you have three windings. Now I'm just showing as an example. The delta connection is when you connected all the windings in series fashion and you close the circuit and you take the outputs at the junctions. So that's what a delta connection is. Let's say you have three windings. I'm connecting in series. These are series connection. I'm making a series connection and I will close this. I will close this connection and I will take outputs at these junctions. So this is a delta connection. It's nothing but similar to this kind of connection where we will get supply from this one. So yeah, this is delta connection. Now with that, I am trying to connect. If you see here, A2, I am trying to connect to B1 and B2 to C1, and I will short A1 and C2. Right? Okay. Yeah. Before joining now, I'm just making sure I'm not short circuiting any big voltage here. So eventually I will connect that, but before shorting A1 and C2, let's see whether our connection is correct or not. So yeah, if you see the phasors now, okay, A1, A2, B1, B2, and C1, C2. So see the A1, A2 parallel to A1, A2. I will just draw it here. The magnitude is of course half of it. Now I have made A2 and B1 shorted. So A2 point is nothing but my B1 point. But if you see from here, this is in this fashion, right? B2, B1 should be this phasor. So I have to draw same in parallel. This is B2, B1, right? It should be in phase with the primary side B phase voltage. So yeah, now this is my A1, A2. Now what is B2 here? Now I have shorted B2 and C1. Now B2 is same as C1. Now how a C1 C2 phasor will look like? C1 C2 will look like this. So yeah, now yeah, C1 C2. So all these three phasors of secondary are in equal magnitude, that is 100 volts, and they are seeming to form a delta kind of connection. So yeah, now the reason why I haven't connected here, because I haven't shorted, because I want to make sure before connecting whether I am shorting a zero potential or a high potential. So if there is a very high voltage, if I shorted this point, circulating currents will flow and the winding might burn, my transformer will get damaged. So if you see, A1, A2, B1, B2, C1, C2 are three balanced voltages. So 100 volts, 100 volts, and 100 volts. Now from the phasor, we have seen that still all the secondary voltages are 120 degrees apart. And now I can say when you take the sum of three balanced voltages which are 120 degrees apart, the sum will always be equal to 0. Right. The resultant will always be 0. That's the basic rule. When there are three different voltages which are displaced 120 degrees, the same magnitude, the resultant will be 0. So yeah, now I can if I connect a voltmeter here, voltage A1 C2 will always be 0 because that's the way I connected my connections. So yeah, that's it. So yeah, I have that. So now we have arrived at a successful delta connection. So this is yeah. So this is a star-star connection, and we have seen how the voltages should be, how the current should be, and we have calculated the KVA ratings as well. And this is a typical star-delta connection. So we now know how to connect a star-delta connection, star-star connection. So with this concepts, and let's go into the solving a numerical problem. Now, please you also please solve with me. I request everyone to take a pen, paper, and calculator along with you, and please solve these questions along with me, so that we will match the answers. Okay, we will see whether I am doing correct, and I will match my answers with you as well. So let's look at the question, and let's see what data they have given and what they have asked for. So yeah, so consider the three-phase transformer. So we were given with the three-phase transformer, and the high voltage side voltage we are given. The line to line high voltage side voltage is given, that is 11 kV, 11 kilovolts, and we were given with the line current in the HV side, which is 10 amperes, and we were provided with the per phase turns ratio. Nice. So we were given with the turns ratio, that is 10. With that data, let me just draw my transformer. How does it look like? And what was asked? We have to estimate the low voltage side line to line voltage if the transformer is of star delta type. So that's the important. So based on connection, based on what kind of transformer, all ratings, all calculations would change. So please make sure, please keep in mind what kind of connection they asked us to do. And first step, you draw the diagram in your paper first. So let me draw it with you. The star delta. So star is my high voltage side and delta is my low voltage side. And I'm drawing the HV side of a three-phase transformer. And what is the connection? Let me first draw them both. Okay. So yeah, this is star connection, right? Let me just A1 into B1, B2, C1, C2, and please you also please draw with me. And one important thing is to mark the polarity. And I'm drawing the supply now. AS, BS, CS, and my second is of delta type, right? Yeah. Okay. Yeah. Now I will take the output at the junctions. That's what the delta connection is. Yeah. So I have drawn my transformer connection diagram, and we will see what values we are given with. So HV side HV side line to line is yeah VHV line to line is equals to 11 kV. Okay. IHV line to line is 10 amps, and one second, someone has joined. Okay. And the turns ratio A is nothing but N1 by N2. I'm just writing it as A is 10. Okay. Now my transformer connection is star delta. Star is HV side, delta is LV side. Okay. So this is just data. I'm just writing it on the side so that it will be useful for my calculation. Yeah. So yeah, what was asked? What is estimate LV side? VLV side line to line. Yeah. Okay. So can someone tell me how to proceed with this kind of problem? Anyone? Okay. See, since my primary HV sending is star winding, in a star in a star connection, my line voltage will be root 3 times of phase voltage, and my line current will be same as the phase current. So with that information, okay, so my VHV LL line to line is equals to 11 kV. This From this I can calculate what is VHV phase voltage. 11 kV divided by root 3. Can someone tell me what's high voltage? Can someone tell me what's the phase voltage? Anyone? 6350.85 volts. Please, everyone, please solve with me so that I can also know that my answer is tallying with yours. Okay. Yeah. So we got high voltage side phase voltage now. And what extra was given? We were given with the high voltage side line current. Fine. Okay. Okay. So I have given with, okay. So we know that V1 by V2 is equals to N1 by N2 is equals to A, the distance ratio. Now, so this implies V2 is equals to V1 V1 divided by A. That means, see, now I know the high voltage side phase voltage, right? Now I want to get the low voltage side phase. I mean, what I want to calculate the induced voltage in the secondary side. So if I have the turns ratio, it will be very easy. Now, what will be my LV phase is equals to VHV phase divided by A. That is 6350.85 divided by 10. Now, this will be 635.08 volts, right? Now, what was asked in the question? We were asked to find LV side line to line voltage. So now we know the phase voltage in the low voltage side. It was asked to phase a line voltage in the LV side. So in the delta connection, both phase voltage and line voltages are same, right? So the required voltage at LV line to line is equals to LV at the phase is equals to 635.08 volts. Yeah, yeah. So it's a simple problem. If you just draw the transformer connection and you write the data what was given, it will be very simple to solve what was asked. So if it just has the low voltage side line to line voltage, if it is a transformer, it is a star delta. If it is a star star connection, we have to multiply the phase voltage with root 3 times to get the secondary line to line voltage. Yeah. So moving on to the next question, we were asked to find the LV side line current if the transformer is of same star delta type. So I'll just write it quickly. Now, what was the current is given? High voltage side L is 10 amps. So high voltage side line to line is 10 amps and turns ratio is 10. Now, since it is a okay star connection, in star connection, my my high voltage side line to line is equals to high voltage side phase since it's a star connection. So yeah, now this implies my high voltage side phase current is equals to 10 amps as well. Now we got this. And from the turns ratio, what would be my low voltage side phase current? It will be high voltage side phase current multiplied by turns ratio. Voltage will be divided, current will be multiplied with turns. So yeah, 10 into 10 is equals to 100 amps. Now I know what is my phase current in my delta side. Now what was asked? Low voltage side line current was asked. So low voltage side line current is equals to low voltage side phase current multiplied by 3. Why root 3 times? Because it's a delta connection. Delta connection, the current will be root 3 times. In star connection, voltage will be root 3 times. So 100 root 3. How much is 100 to 3? 1.732 into 100. 173 something. Yeah. 173.2 amps. A simple one. The same thing which we did for voltage, we will do it for current. Okay. Okay. Now we have to estimate the kVA. So whatever may be the kVA type of connection we discussed just now. To calculate the kVA, it doesn't matter what kind of connection you are doing it in. Even it is star 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 delta anything. My kVA formula will be, what is the formula? Root 3 VLL ILL. Now let's calculate from the primary side. Primary side is HV side. Root 3 into, what is the VLL in HV side? VLL in HV is 11 kV and current is 10 amps. 11 into 10. How much is this? Okay, I have got 190.525 kVA. Okay, now let's tally it from secondary side as well, which is LV side. What is the low voltage side line to line we got? Low voltage line to line, this answer in first question, 635.08. Okay, 635.08 volts into, what is the line voltage in LV side? This is the problem. Line voltage in LV side, 173.2. 73.2. So can someone calculate this as well? 635.08 multiplied by 173.2 into root 3. We got 190.518. See, almost same, because we have neglected some decimal places. That's why we are getting this. Anyhow, we got the same kVA. So that's why you calculate a kVA. If you're asking, just to do root 3 VLL ILL, and you can tally it from both primary and secondary side as well. Okay. Now we were asked to calculate LV side line to line voltage in the transformers of delta to star type. So it is same kind of connection, but it same kind of problem, but the connection is different here. Let me just draw it quickly. It is a delta connection. So my supply is, so supply, and the secondary is, okay. So here you can see it here. Same point anyway, supply, and my secondary is star, yeah. And this will go to the load side. Okay, so yeah, let's say this is a delta star connection, and we have to estimate LV side line to line. Okay, this was asked. So see, what was the HV side line to line voltage? It was 11 kV. So in a delta connection, my line to line voltage is same as phase voltage. So my HV side phase voltage will also be 11 kV. And what else information we have? HV side line to line voltage current is 10 amps. So for a delta connection, my HV side phase will be 10 by root 3 because it's a delta connection. Star and delta phase and line are not equal. So how much is 10 by root 3? 5.77. 5.773 amps. Okay. So what was asked? LV side line to line voltage, right? So LV side phase voltage, let's calculate that first, is equals to HV side phase voltage divided by turns ratio. That's a transformer principle. So 11 kV divided by 10. How much it is? It's 1100 volts. Now what was asked? VLV line to line. So since my secondary is a star connection, my line to line voltage will be root 3 times of phase connection is equals to root 3 into 1100, which is 1905.25 volts. Okay, yeah, this is again a simple connection. Once you draw the circuit connection, it will be very easy. So same thing, now we have to calculate the LV side. What was asked? Low voltage side current, line current. Okay, now we just calculated HV side. Okay, I'll just write it again. HV side line to line current is 10 amps. This HV side phase will be 10 by root 3. This is 5.77 amps. Okay, now LV side phase current will be HV side phase current multiplied by turns ratio. Now it will give 57.7 amps. Now you were asked to calculate LV side line to line, but since it's a star connection, my line to line current is same as phase current, which is 57.7 amps. Again, a simple problem. So yeah, the final question for today is KVA. Total KVA is equals to root 3 VLL ILL. Now again, let's solve this KVA from both sides. Now my primary side is HV side. Root 3 into VLL HV. It is 11 kV and ILL HV is 10 amps. It will give me how much? Same thing anyway. Root 3 into 11 into okay, same thing, 190.525 kVA. Now from the secondary side, if you see low voltage side, root 3 into line voltage in low voltage side, how much we got? Line voltage in low voltage, it is 1905 point, how much it is? 1905.2. Okay, 1905.2 multiplied by line to line current in LV, it is 57.7. Let's see whether we are getting the same answer or not. Some calculate for me quickly. 57.7. Okay, yeah, we got 19.404 kVA. Again, if you don't neglect all the decimals now, we will get exactly the same kVA. So it's tallying, it's not a problem. So yeah, that's how you solve a transformers problem with multiple kinds of connections. Like whatever connections maybe they're asking, whether they are star star, star delta, delta star, any kind of connection, I will suggest you to draw the circuit first. That will solve 50% of the problem, and then you just see what data we were given, and what should be the line voltage, what should be phase voltage if it's a delta connection, what will be the line and phase voltages and currents if it is a star connection. So such basic things you just keep in mind while solving the connections, and it will be very easy. So let's have a quick summary of what we have discussed today. We have started our discussion with three-phase transformers, how we can construct a three-phase transformer with three single-phase transformers of known ratings, and we saw what should be the rated voltage should be applied so that my windings won't be overloaded, and we saw the phasor diagrams of the same primary windings and secondary windings, and next we saw how we can calculate kVA ratings of the transformers, and if at all I connect a balanced load, how what are the currents my winding should draw, and the restrictions on the currents we have discussed, and we also saw the basic star to delta kind of connection, and the phasor diagrams of it, and yeah, how to connect a successful delta connection, that also we saw, and based on the concepts we have solved a simple basic problems of two different connections. We have solved the problems for star delta and delta to star as well. Yeah, so if you have any doubt in the topics we discussed today, please do ask me, and let me know if you have any doubt. And the last week, one of the student have asked whether there are solutions for assignments. So I checked the portal myself. So this year portal, they already uploaded the individual assignment solutions. So if you see your course portal in the leftmost column, if you go to the bottom, there is detailed assignment solution tab. In that you can find the detailed assignment solutions question to question for the completed assignments. Whatever assignments you have completed, you can find the solutions there. So yeah, I request you to see that. So I think you are not today in the session. So whenever you saw this recording, I want you to go to that tab and check the solutions tab. So if you are not finding it still, you please mail me. I will send you the individual assignment solution PDF copies as well, and I will also inform to the team if your portal is having any glitch. So yeah, if you have having any doubts, please ask me. And please do join the session for which will be starting from 7 p.m. today. So there we will discuss some other topics which we are not discussing today in this session. So I have discussed only kinds of connections. So there some more additional concepts will be discussed in 7 p.m. session. So that will also help you to solve the assignment problems eventually. So I hope this session is informative to you all, and if you have any doubts, keep mailing us. Keep dropping your questions in the discussion forum. We will address them individually. So if there are no more doubts, then I will end the session here now. Thank you everyone to attend for attending the session and staying patiently.